This conference will now be recorded.
Very good morning, everyone. Today, we're continuing with system of particles and rotational motion. So we have been discussing about center of mass for various objects. So today, we'll pick up problems from the part of rotational motion, moment of inertia, etc. So here it will be moment of inertia and rotation. So this part we'll see today here in this discussion. So we have picked up problems from previous year's JEE paper. So suppose this problem is actually JEE 2006 paper from 2006 paper. Okay. So we'll first go with simpler problem, then we'll go to harder and harder problem as we go along. So the first problem is saying that a solid sphere of radius capital R has moment of inertia I about its geometrical axis. So when this geometrical axis is said, what axis you should take? This axis you should take through the center of mass of the object. In this case, solid sphere has radius capital R and its moment of inertia is given as I about its geometrical axis. That means the moment of inertia about center of mass for the solid sphere. And this moment of inertia for a solid sphere is actually 2 by 5 if the mass of the sphere is capital M, then M r square. This is the radius. R is the capital R is the radius. So sometime we need to remember some of the results like moment of inertia of various geometries like thin sheets, thin disk, ring, then about various axes. At least about center of mass we should know. Then rest of the things can be found out by using parallel axis theorem or perpendicular axis theorem. So in this case, the moment of inertia of a solid sphere is given as I, which is about center of mass, and that is actually 2 by 5 m r square. This derivation has been done in the class, so we are not deriving it, we are just using the result itself. So the moment of inertia of a solid sphere about an axis passing through center of mass is given by 2 by 5 m r square. R square is the radius of the sphere. It's it is melted to a disk of radius smaller. So this sphere is actually melted to a disk, of radius smaller, as you see here, and thickness T. So when you say disk, you see here disk actually has certain thickness. This thickness is T given here. Okay, it has area into this thickness, so it has certain volume also. So if its moment of inertia about the tangential axis which is perpendicular to the plane of the disk, as you see here, this is the tangential axis of this, like this is an axis which is tangential or tangent to the disk, and it is perpendicular to, so tangent can be of two types. See, one tangent can be like this, it is in the plane, tangent in the plane, and this is tangent in the perpendicular direction of the plane of this plane of this disk. So tangent can be drawn in two ways, parallel to the plane and perpendicular to the plane. Here this tangent is perpendicular to the plane, it said. Okay, so what is happening here? Solid sphere was there, then it is melted to a disk. The disk has radius. Disk has radius smaller as you see in the figure, and it is said that the moment of inertia of the solid sphere is I, and when the solid sphere is melted into disk or of radius smaller, its moment of inertia about an axis which is tangent and perpendicular to the plane of the disk, as you see here, will be same as this. Okay, for solid and for disk both are same when it is along the axis, along the center of mass, so which I have already written for solid sphere. Now we have to write the center of moment of inertia for this particular disk. Okay, about this axis, this is tangent to this disk and perpendicular to the plane of the disk. So this we can find out. See, we know the moment of inertia above center of mass is mr square. If this is smaller, for a disk mr square by 2, sorry, not mr square, mr square by 2. For a disk, moment of inertia about an axis passing through the center of mass, this point, is mr square by 2, and this has a distance r because it is at the end. This is tangent to this, and mass of the disk is suppose the same m. So you have to actually add this thing mr square. So this is actually parallel axis theorem. So using parallel axis theorem, we can find out the moment of inertia of the disk, that is mr square plus mr square by 2. This is about center of mass, and this is the mass of the disk and square of the distance from the center of mass to the axis here. So this will be 3 by 2 m r square. Okay, this is for a disk. Now, according to the question, this these two will be same. Then you have to find out the value of this small r. Okay, value of the radius of the disk you have to calculate. So let us just equate these two. So 2 by 5 capital M r square is equal to 3 by 2 m smaller. You might be thinking why these masses are same. Anyway, the same sphere has been converted into a disk, so mass is not going to change. So both this disk and the solid sphere will be having the same mass. So we can strike out from both sides. So we have to find out r square. Small r square is equal to 4 by 15. This is into capital R square. So R will be 2 by square root of 15 into capital R. So this is the answer. So first option will be the correct answer for this question. Alright, so it was nothing, like it was very simple problem. What you need to know is you need to actually know, or you need to remember, or somehow you have to find out the moment of inertia of the solid sphere about its center of mass, about an axis passing through center of mass, and you need to find out moment of inertia of a disk about an axis which is tangential to the disk and perpendicular, that axis is perpendicular to the plane of the disk. So that can be found out by using this parallel axis theorem, and if you equate them you will get the answer. Okay, we'll go to the next question. So this question is being asked in JE 2012. Okay. Question. Let us read the question. Two cylinders P and Q of same masses are same, and same radius start rolling down a fixed inclined plane. So there is an inclined plane. Suppose this is in. Sorry. Let me draw it properly. So there are two cylinders. I'm just drawing only one for the representation purpose. So this is a fixed inclined plane, and see inclined plane has a fixed height, some h or small h you say, small h, and this has certain angle theta. So two cylinders, their masses are same, their radius, no, the same radius, yes, radius also same. Okay, start rolling down a fixed inclined plane from the same height at the same time. So from the same height, same time, they are just they start rolling down. Rolling means it will be coming like this. Okay, like this. All right, so it is rolling down. Cylinder P has most of its mass concentrated near its surface. Look, this is a cylinder. Suppose P, radius must be the uniform. So here, if the most of the masses are concentrated surface, at the surface, most of the mass concentrated at the surface. Okay, suppose this radius is smaller, and another cylinder. So this was with the P. Most of the mass is concentrated at the end or the surface. I have another cylinder Q, right? So this Q, they both have the same radius anyway. But in this case, the problem is little different. The most of the mass is concentrated at this region, or very near to the axis, very near to the axis. Most of the mass is concentrated very near to the axis. Then which of the following statement is correct? Let us read the statements also. Both P and Q reach the ground at the same time. Okay, we have to check whether they will take the same time or not. Then cylinder P has larger linear acceleration than Q. Then both cylinders reach the ground with the same translation kinetic energy. Then option D says cylinder Q reaches the ground with angular speed, larger angular speed. Q reaches the ground with larger angular speed. So there are few informations we need to actually find out uh, from these two cylinders P and Q, whether P and Q reaches at the same time. So this is actually uh, this we will say later. First, let us see other options. P has larger linear acceleration than Q. See, when a cylinder or any object rolls down, okay, it has both rotational and translational kinetic energy. So from the conservation of energy and all, if we consider, then we'll see that the linear acceleration, linear acceleration linear acceleration of the object. Have I left? Okay, no. So linear acceleration is given by A is equal to, for in general case we are saying g sine theta divided by 1 plus I divided by m r square. Okay, so this I is actually, this I is the moment of inertia of the object. This small r is actually radius of gyration. From that concept it will come. Anyway, this you take as the radius. Okay, take this r as the radius. G, gravitational constant, like acceleration due to gravity. Theta, sine theta, you will be able to get from this theta. I is moment of inertia for a particular, if it is sphere, then it will have some value. If it is disk, it will have some other value. And if it is cylinder, it will have some other values or expressions for I. So basically this thing you should remember. Now look here. See, what is moment of inertia? Moment of inertia is actually is defined as m r square. Okay, what does this mean? M and r square. What is this? This is the mass. And what is this r square? It is the distance square from the axis of rotation to the axis of rotation to the distribution of mass. If the mass is distributed at the surface, then it's this distance. Let me say distance square. So this distance will be actually radius. Okay, this distance will be radius. Okay, but in this case, look, this mass is, most of the mass is concentrated near the axis. That means what? This distance is small. Okay, so if this is p cylinder for which most of the mass is distributed at the surface, then moment of inertia for this, suppose this is md1 square, and for the other one where the mass is concentrated near the axis, md2 square. So you look, this d1 square is much greater than d2 square because the mass is concentrated very near the surface. So that's why moment of inertia for the p cylinder will be greater than the moment of inertia for the cylinder q, because it has mass distribution near the surface, sorry, near the axis. Okay, now look, this expression for the acceleration. Expression for the acceleration, you look here. If I just consider acceleration for, so this is linear acceleration for p. What is linear acceleration? This one for p cylinder. See, if I just put the values and all, I'll get anyway. But I just wanted to make a comparison with AP and AQ. See, AP, that means here you have to write IP, and when you write AQ, you have to write IQ. Since this IP is greater than IQ, okay, so the moment of inertia, will be, okay, I have written that moment of inertia is greater in case of P. So if this denominator is greater, then the whole quantity will be lesser. So that's why the angular acceleration for Q cylinder will be more than the P cylinder. What is the logic? Logic behind this is that the moment of inertia for P is greater than the moment of inertia for Q. And if you have a greater quantity here, then the whole quantity acceleration will decrease. So that's why we can say if this is true, then Vp also will be less than Vq. If the linear acceleration is less for a for the P cylinder, then for the same cylinder, for the Q cylinder, the velocity is greater. So what I'm trying to say is that since the acceleration is greater in case of Q, then the linear velocity also will be a greater quantity with respect to Vp. Okay. Now come to the point here. Both P and Q reach the ground at the same time. This is not true because see Q has greater linear acceleration and also greater linear velocity. So that's why Q will reach faster than P. Okay, so the first option is not correct then. The second option says cylinder P has larger linear acceleration than Q. No, we have seen that linear acceleration for Q will be greater than P. So this is also not true. Both the cylinders reach ground with same translational energy. This is also not true because see, translational kinetic energy actually related to this velocity. Okay, linear velocity. If the linear velocity is not same, see, linear velocities are not same for both. So why? How then the translational kinetic energy for both of them will be same? No, it is not true. Then last is cylinder Q reaches the ground with larger angular speed. See, I'll erase this portion to analyze the fourth point. So we have seen that linear acceleration for Q is greater than linear acceleration for P. Then you know uh, linear accelerations a okay, let us go with velocity, linear velocity, speed, linear and angular speed. So then VQ linear speed must be greater than VP. Okay. So from here, look once again. VP VP is equal to R omega P, say omega Q. That means you know the linear velocities are directly proportional to omega P. So we can see since the angular velocity is directly proportional to the linear velocity, so the angular velocity for Q will be greater than the speed of angular speed of P. So this last option will be the correct option here. Correct answer for this question will be the last option. Then, so this is the correct answer. You have to find out. Uh, yes, so this you can find out because BP is less than BP is less than VQ, then omega P also will be less than omega Q. Okay, omega is angular speed. Now we'll move on to the next problem. This is also a very, very interesting problem. The problem says that a hoop of radius r, a hoop of radius r and mass m rotates, rotating with an angular speed omega 0 is placed on the rough horizontal surface. A, like the initial velocity of the center of the hoop is 0. What will be the velocity of the center of the hoop when it ceases to slip? When it ceases to slip? That is the question. So here actually the maximum friction acting at the bottom or at the contact point will convert the backward slip into a pure rolling motion. So the torque of this friction about the bottommost point will be 0. The situation is actually like this. Sorry. Initially, center of mass had 0 velocity. Then the velocity suppose becomes v. So there was a hoop of radius smaller, mass small m, with angular velocity omega 0. It is rotating. The initial velocity of the center of hoop is 0. What will be the velocity of the center of hoop when it ceases to slip? So actually this can be found out from the conservation of rotational kinetic energy and momentum. Okay, from the conservation of angular momentum, we say from conservation of angular momentum. From the conservation of angular momentum, what we can write is m om, m r square omega. Okay, or m omega square r. Sorry, m m also this will be initial This is equal to m MVC, center of mass, momentum of center of mass, and I omega. Okay. So what is this I here? I is actually moment of inertia of the hoop, that is m r square. And what is this omega? We can write V by R. If we put this here, if we put this plug here, then we'll see what we get. M R square omega naught M R VC plus I omega. I is M R square, omega is V by R. So M goes, one R also will go. So what we get actually R omega 0 . So this will be actually MVR again. MVR1 goes, so it will be, so this VC actually VC MVC VC plus this is actually R goes MVR. Okay, MVR here MVCR. This omega 0, okay, I think I have done a small, okay, so here there was this, so this there will be no R, because this is R, one R I have striked out, so this will be simply let us write V, and along with M, or we can just strike this M also, so we get actually 2V is equal to omega naught R, omega naught or R omega naught by 2. So R omega naught by 2, this will be the correct answer. So we have actually used conservation law of angular momentum, and from there we have solved this problem. Okay, so next we'll pick up another problem. So let us just write down the problem first. A thin disk of mass capital M and capital R, radius capital R. A thin disk. So this is question 4. A thin disk of mass and radius capital R. Capital R has mass per unit area. Mass per unit area. Mass per unit area given as sigma r is equal to k r square. K is a constant, proportionality constant, and r square is the distance, where r is the distance from its center. R is where r distance from the center. From the center. Now, its moment of inertia about an axis, its moment of inertia about an axis going through its center of mass, going through its center of mass, and perpendicular to its plane. Perpendicular to the plane. Okay, plane. All right. So you have to find out this is there are options given mr square by 2. B is mr square by 6. C, option C says mr square by 3. Option D says 2 mr square by 3. 2 mr square by 3. Okay, we'll try to solve this. So a thin disk of mass capital M and radius capital R has mass per unit area which is varying with respect to distance is given, where R is the distance. So you look, this is a disk. So the mass is actually varying point to point. So that is what is said here. Okay, small r is the C center to its distance. Okay, now for this kind of mass distribution, when the mass distribution is not a constant or uniform, when it varies with distance, then what will be the moment of inertia of this particular thin disk? Thin disk about an axis which is passing through the center, and it is uh, perpendicular to the plane. So let us go to a simple open place, like see here sigma r is equal to k r square. Okay, so in these cases, if you want to calculate moment of inertia, what will be your first job? For a disk, suppose this is a disk, I just consider an element like this. So this is having this radius. Suppose this thin, the elemental disk has radius small r, having certain thickness dr. Suppose having thickness dr, I'm just considering a thin disk. So you have to actually find out the total mass Total mass, how to find out this total mass? Total mass has to be found out rho into dv, okay, integration of dv, okay. Anyway, rho is constant here. Rho, okay, this is disk, so it is not rho, neither it is, so this will be dA, area of the disk, and this is sigma. Sigma is the mass per unit area. So mass per unit area. So in this case, see what is this elemental area? 2 pi r and dr. Sigma is given. Now you have to do the integration part with respect to r to find out total mass. So total mass will be capital M, which, see, for radius small r, the limit is 0 to capital R. Okay. Now see what is this sigma? Sigma, we can write it down. Let us not take in outside the integration because there are k here. So k r square, and this is sigma, k r square is sigma, so it goes from 0 to capital R. Okay, and what is this area? 2 pi r and dr. This is the area. So if we just integrate this, what we get? See r, this r, so this is r cube, so k 2 pi k. So from here, 2 pi k by 4, and this is capital R to the power 4. Okay, so what is the mass then? What is the mass? See, mass will be 1 by pi, so half into pi k r to the power 4. So this is the total mass of this particular disk when the mass per unit, or this is surface mass density, varies like this. So we have got the total mass, so no worry. Now moment of inertia about center of mass. So moment of inertia of this disk about center of mass can be written as r square dm. If I think a small elemental this this, okay, if I this, so it has radius, suppose it has radius up to small r and mass dm. So what is this dm? Now here also, so this is there is actually integration involved in this case also. So r square, what is dm? Sigma into 2 pi r dr. Okay, so this is the mass. So sigma will be written again here, and limit should go from 0 to capital R because it has capital R radius. See, this is r square into k r square, the value of sigma, and you have again 2 pi r into dr. So if you just put the, like, if you can do the integration, that will be giving you, so 2 pi k, let us 0 to capital R, so r square r to the power 4, and this is r to the power 5, r to the power 5 dr. So this would give you actually 2 pi k by 6 into r to the power, capital R to the power 6. Okay, so this, see, we can actually make use of this particular value, capital M, 1 by, so pi k r to the power 4 by 2. Let me just uh, arrange that part. See, this will be this, right? So pi k r to the power 4 by 2. Okay, if I just write this, okay, that means you have to multiply 2 over here, and we have 3 down, and r to the power r square, again we have r square. So look here then, so this particular thing is given as capital M, that is the mass of the disk, and this is r square. So finally you would get the moment of inertia of the disk about its center of mass itself will be 2 by 3 m capital R square. I'll just simply repeat it. When the mass distribution is not uniform, when the mass distribution is not uniform, it varies with space or with distance, then what you would do first, you have to find out the total mass of the disk. How? Just by integrating it. Okay. The problem was given that total mass is capital M suppose, and radius is capital R. So the answer is this D, 2 by 3 m r square. This option will be the correct option. Okay, this is 2 by 3 m r square. So you have to first find out the total mass of the disk, then you have to write r square dm and integration 0 to capital R to find out the moment of inertia, thinking that you just think an elementary disk which has radius r and thickness dr, and if you integrate that by taking for 1, if you just sum over all of such disk, then you get the moment of inertia for the whole disk. Okay, so we'll try to take one more problem. We'll try to take one more problem. This is 2019 problem from 2019. This is actually rotational motion we are doing today, and moment of inertia. So rotation and moment of inertia, moment of inertia. We'll take one more problem. This is a very short problem. So I'm not writing the whole problem. Let me write in short. You can just listen to me. The time dependence of the position of a particle of mass m is equal to 2. So time dependence of a particle, sorry, if time dependence of position of a particle, time dependence of position of a particle of mass m is equal to 2 is given by r of t. This is a vector. R of t is equal to 2t I cap minus 3t square j cap. 3t square j cap. Its its angular momentum. Its angular momentum. Angular momentum. Its angular momentum with respect to the origin, with respect to the origin, at time t, at time t is equal to 2 seconds, say, is options are. So you have to find out the angular momentum with respect to the origin. Angular momentum means there should be some axis of rotation. So it is passing through, suppose, the origin. Okay, so the angular momentum with respect to origin is given as 36 k cap, or B is minus 34 k cap minus I cap, or C, option C is saying minus 48 k cap, or option D is saying 48 I cap plus J cap. Okay, you have to find out the correct option. So let us write what is angular momentum. Angular momentum is actually R cross P. What is P? P is the linear momentum. Okay, so linear momentum, let us write linear momentum m v. V is a velocity vector and this is mass. So m into R cross v. So R cross v you have to find out. Since this R is time dependent, so finding v will not be a problem. So this will be dr dt. So that is 2 I cap minus 6 t j cap. That's all. Okay, 60 j cap. So we have got velocity, we have got position. So we have to find out the angular momentum from this expression. So we have to basically do R cross B. Okay, let us go to the next page. So L, angular momentum will be M R cross B. So this M, let it be like this. We have R vector as 2t I cap minus 3t square j cap, and we have v vector. We'll write directly what we have got just by taking derivative of this part, time derivative of this part. So this was 2 I cap 6 6t j cap. Okay. Now let us do the cross product. So cross product R cross B will be, see, ij2, this is two dimension, so I'll write ij. So 2t here minus 3t square, here 2, and here minus 6t. So I cap, actually this is two component, so it is not that useful. Okay, so let us do directly. Three component will be effective determinant. Excuse me. This is I cap, so this will give you 0. So you have 12 t square ij k. So this will give something. So this will be again 6 t square. Ji means minus k. Ji minus k. So this will be plus k cap. So now m is 2 and t is 2. If we put that, then L will be putting this 2. L will be 12 into, sorry, this is 2, this is, oh, here there will be minus sign here, minus sign. Okay, so this is 12 and this is 4, so this is 12 into 4, this is minus sign, here it is plus, this is 6 into 4, so this is 24, this is k cap, so this is 2 into 48 minus this 24, so this is 24, so it will be actually 48 k cap. Okay, oh, here there will be minus sign with this, so it will be minus 48 k cap. This was very simple. R cross B, that is the main point you have to find out, otherwise things are all right. Okay, so with this we'll stop it here. Next class we'll take more harder problems. So bye for today.